usually do. Welcome, everyone. On behalf of the Energy Systems Engineering Institute and the section, Lehigh Valley section of the IEEE, we'd like to present today our speaker, Mr. James Daley. A brief bio about him. Mr. Daley is now currently working as a consultant, having retired after 37 years with ASCO Power Technologies as a division engineer. He is a life senior member of IEEE and a member of the Tau Beta Pi Society. He has a bachelor's degree in electrical engineering and a master's in engineering management from New Jersey Institute of Technology. And he's accumulated now over 50 years of experience in the generation, distribution, and control of power on the user side of the meter. He's authored IEEE and SAE transactions and other papers on the issues surrounding customer-owned generation and holds a number of patents and design innovations in that field. With regards to today's presentation on the 1547 standard, he's a member of the writing group for that standard and has held chair and co-chair in the writing group positions for the full breadth of this family of documents. He's currently working with IEEE on the development of a standardized interconnection protocol for industry-wide adoption. So with that, I'll hand it over to Mr. Daley for a presentation.
I'm tired. Didn't realize I did all of that. Anyway, this presentation I gave to the local chapter of the IEEE. We had a meeting last May and we talked about the standards process for the interconnection. I've been coming to ESCI for the last 2.5 to 3 years now. And a lot of the presentations we've had are on renewable energies, on solar photovoltaic, and how you do it for villages in Africa and so on. And a lot of that is interesting. But there's a big impact that distributed energy has on the grid in this country. When we started in the early 90s to write the standards, the concern was by manufacturers, we need a standard set of protocols to interconnect. The concern was by utility companies, we don't want anybody on there that we don't know how they're operating or what they're doing. And the concern was by regulators, we got to have renewable resources connected to the grid because we can't continue to use widespread fossil fuels. So, there are a lot of conflicting interests. And when we got together at the first meeting, I started attending it when draft 2 of the original standard was written. There were over 300 engineers, regulators, and lawyers in this working group. At any meeting, we had at least 150 show up. Now you can imagine what it's like to get 150 engineers and lawyers who agree on anything. It took 9 drafts for us to get the standard issued. So that's kind of like the background on this. The electric grid is comprised of basically 3 functions. You have generation, you have transmission, you have distribution. In generation, there are several different sizes. If you talk about nuclear and coal-based generation, you're typically talking about baseload generation. They're on 24 hours a day, 7 days a week. It takes months to turn them on, it takes months to turn them off, so they form the base generation. They're running 8,760 hours a year. You have intermediate generation, which is typically generation that you can throttle the output of. Gas-fired turbines, oil-fired turbines. Something you can bring on the line quickly and take off the line. One of the advantages of using this intermediate generation with gas-fired turbines is that you can recover energy from the exhaust of the turbine and do what's called a combined cycle plant, where you create steam with that exhaust and you run steam generators to produce electricity too, and it boosts the efficiency of the plant upwards in excess of 60%. Peaking generation comes on only when you have a real demand, like on a hot day in the summertime or a very cold day in the wintertime, if you're a winter peaking unit. And they only run for a couple of hours. and they're typically gas-fired turbines. A gas-fired turbine typically converts about 22 to 25% of the energy content in the unit of fuel to usable shaft horsepower. So you can see it's pretty inefficient, very expensive to run. The kilowatt hours produced are very costly, plus the fact that the only time you're making money or return on the investment in this machine is when it's producing energy, and it's only doing that upwards of 200 hours a year. So it's a very costly investment. And you have hydro generation, which is pretty good, except dams are very expensive to build, but once they're built, operating costs are usually pretty low. But there's only a few places in the country where you can use or can install hydroelectric. Transmission systems are interstate. They really are what the grid is. These huge transmission lines that run. We have one that comes from Niagara from Robert Moses Power Vista up there, down across New York and across New Jersey, down, and I think it terminates in Somerville, is the last substation on that transmission line. So they run great distances. When you fly across this country and you look at the land out west and how much of it is uninhabited, you can see miles and miles and miles of transmission line. That generally is how you move your bulk power. The problem with generation is base load generation needs water. So it's got to be near a river or a huge man-made lake. So you can't really put it in the middle of a city where the demand for electricity is. So you generate out where you can get the water and the fuel to it, and then you ship it into the city, and it comes in on transmission lines. Now, the transmission systems are generally operated by what are called RTOs, Retail Transmission System Operators. They're the ones who decide which lines they're going to use and so on. And then finally, we have the distribution system. This is the pole that runs down the street. It's the substation that you drive by on the highways. It's where your transmission lines terminate into, and then it spreads out into all these radio feeders going to the various neighborhoods and infrastructure and whatnot. This is also where the smart grid thing is going to start being used. Anybody have an idea what the smart grid is?
Basically, the smart grid is a system of wide area monitoring to more accurately do demand response for, so you can waste less power and generate exactly what's being used.
The system already does that. The system is a real-time energy system. Energy in equals energy out all of the time, or you got problems. Smart meter or smart grid is that up until now, all of your energy is measured at the generator and at the substation. But all of your use is below the substation. So what the smart meter does is it enables you to find out where the energy is being used below the substation. And when you run into difficulties in various areas, because over half the outages and faults that occur on the distribution system, it enables you to determine immediately where the outage is, because the meter that's without power calls and says, hey, I'm without power. Right now, the way you find out that you don't have power in the section, or you've had a failure, is that somebody calls you and says, hey, I don't have power. Then you wait for somebody else to call, and somebody else to call, and they say, okay, let's map that. All right, this is where the problem area is, let's send a crew out there. But the smart meter measures the power at the point of use and goes back to the utility company and says, here's what's going on. Another advantage of that, and this is the big plus, is that that meter can be shut off by the utility company. That doesn't sound like it's a real advantage, but what happens if you get into a situation where you've got excessive demand in an area, you need to reduce that demand? Well, the first step you take is to start shutting off load. Today, the first step that they take is they wait for the frequency to drop, and then they start cutting off big chunks. If you have meters that you can control, you can selectively get in there and reduce that demand and do a much better job of controlling your environment. There was a fire in California a couple of years ago, and as a result of that fire, some transmission lines ran into difficulties, and they lost 1,178 megawatts in one step. Now, can you imagine an electric utility system where power in equals power out all the time, and all of a sudden you lose 1,200 megawatts in a section of that grid? It has a tendency to disturb things. So what the smart grid is able to, what the smart grid will be able to do is that when it sees that I've lost this section of power and these units are offline, first of all, it will be told which ones have gone off. And with some selective programming and whatnot, you can put in some kind of an autonomous response to that that gives you a growth response that will help to keep the system up and operating. Okay, distributed energy resources. Let me first say what they are. Solar photovoltaic, you're aware of that. Wind, you're aware of that. Bio, some hydro, some geothermal. It's basically renewables. The problem with the broadest category of renewables, solar photovoltaic and wind, is that it's not constant. It varies. It varies second by second. And it's a function of wind volume and wind speed. It's a function of suns and clouds and that kind of thing. So it varies up and down, and it has an impact on how you plan the operation of your system. The independent system operator, when he gets his bid in from all the guys who are going to generate, he determines who he can count on. And if you look at the Federal Department of Energy's webpage for the Energy Information Agency, EIA, and look up for cost of generation, in that table they will tell you what capacity allocation is given to each type of generation. Gas turbines, nuclear, coal, they're given 95, 96% capacity. Solar, 25%. Wind, 35%. So if I have a 100 kW solar farm, and I tell the ISO I'm going to come online tomorrow, it's going to be a sunny day, so I'm going to bid in to provide energy, he's going to say, okay, I'm going to count on 25 kilowatts from your 100 kW station, because that I can pretty much count on being there. If I get more than that, hey, I'm ahead of the game, but I'm going to count on that. You're going to get paid for all you produce, but he's only going to give you an allocation of 25%, because that's the reliability of it. There were several pieces of legislation approved over the years. Back in the early 70s, it was PURPA, the Public Utility Regulatory Policy Act. And that was passed because we had an energy problem at that time. And energy efficiency could be improved if plants, which are now called combined heat and power, CHP, where I mentioned before about a combined cycle generating plant. Well, an owner of a building can put in a combined heat and power system where he takes the heat off of the prime mover and uses it to produce hot water or steam. A lot of hospitals do this because they have a tremendous need for hot water. And you can get heat from a prime mover to heat water for your domestic needs very cost effectively. In fact, some of their efficiencies will run as high as 72, 73% of fuel to energy conversion in that CHP plant. So it's a very cost-effective way to meet your energy needs, particularly if you have a high need for energy. how we went through these. We have, over the past decade, 2 decades, tremendous growth in solar, and it has an impact on the grid, but there are also tax incentives that go along with it. There are many requirements that govern how you interconnect. You just can't take your solar panel and connect it to the grid and say, okay, I'm good, because it has an impact on the system. And so the individual utility companies, they want to be assured that whatever you put on their grid is safe and doesn't have a negative impact on their system. So you have the utility regulation requirements. You have state regulators who tell the utility companies, you need to do it, but we'll approve what you told us how you're going to do it, because it makes sense and it provides safety for your people and for the system. Then you have building codes such as NFPA 70, which is National Electric Code. Then you have the IBC, which is the International Building Code. And there are other drivers that impact how you put these things together. But all of them have a say as to what the system is going to eventually look like. There is a lot to be gained from product standardization. How many of you guys are going to go into product design and product engineering? Oh, God. How many are you going to do software? Firmware? Are any of you going to be in electrical engineering? Okay. There is a need for standardization of products. There are international standards that govern how you design a product, what makes that product safe, what makes it cost effective, what are your production capabilities, what is your production process. All these things have to be looked at. And they all start with looking at standards. Now, initially, the standard that we developed was 1547, and it inputs, as I said before, from utility, industry, academia, and governments. There were 11 drafts to reach the final document on the initial unit. The committee that's responsible for this had 19 members, and the working group had 347 in the working group. And that was a real challenge to keep them going in the same direction. The family of documents, is 1547, is a standard. It's the base document. It says what are the functional requirements for interconnecting a distributed energy resource with the electric grid. 1547.1 is a conformity assessment standard. It says that here are the methods and procedures and processes that you have to put the products through and certify that they have met the functional requirements of 1547. The rest of the family, .2 through .8, are guides and recommended practices, and that's where the 340-some guys all got their words in as to, I want this special consideration, I want that special consideration. But because they are pretty finely focused, it doesn't make it into the standards. It says that when you've got this kind of a situation, these are the things you want to think about. The standard is an interconnection standard. It doesn't pertain to the distributed energy resource, and it doesn't pertain to the electric grid. Only the interconnection. What is going on at the interconnection? The technical requirements. Initially, thou shalt not regulate voltage at the point of connection. And you can understand why. If you're got a system connected to the grid and you're attempting to regulate voltage, the grid operator has line regulators and capacitor banks that it uses to regulate line voltage in the system, and the two things start to fight each other. It has to integrate with the grounding. I was just talking with David as we started here. A significant impact is how is this system grounded, where is it grounded, and what kind of detection do you have on it. Synchronization, if it's an inverter, it's usually not a big issue. If it's a synchronous generator, you have to synchronize, but it's a relatively simple thing to do. Then there are considerations for where you connect at the distribution system. There are subsurface of the distribution system called secondary grids and spot networks. And these are what?
Inverters and spot networks, oh my.
How about at area grids, at area networks? Well, if you get into networks, you find out they're a unique distribution system that carries its own special considerations. And there was a lot of consternation about interconnecting distributed energy at a network. But I've done it at both spot and grid networks over the decades, and if you do it right, it's not a problem. The problem is it has to be done right. The biggest concern that comes out of this whole system is being able to detect an unintended islanded system and disconnect from it. Do you know what an islanded system is?
It's a system
Okay.
that doesn't operate.
I'm sorry?
It's a system that operates like separate from the grid.
Yes. And an unintended islanded system is if you got a nice sunny day going and your system's feeding power into the grid and all of a sudden the grid disconnects and leaves you hanging out here. You got to be able to detect that and disconnect from the grid. And it's important that you do that quickly for equipment protection and for personnel protection. You don't want to be feeding power into an area of the distribution grid that the utility company thinks is dead, because that kills linemen, and that's not a good thing to do. It was also concerned with being within bounds on voltage and on frequency. There is a standard, ANSI, American National Standards Institute, C84.1, which says that a utility company is required to provide voltage at the point of common coupling within minus 10% and plus 5% on a regular basis, with excursions outside of that, momentary excursions outside of that to some limit. So if the voltage goes below the acceptable point, the original thinking was it should come off the line. Your distributed energy system should come off the line. Similarly with frequency. The impact that the variation in frequency has is that many of your distribution protective scenarios or strategies are that if I see a reduction in frequency below some trigger point, I'm going to shed load so that my generation has a chance to recover. So when you start now putting distributed energy systems in there and your frequency starts going down, if you pull that energy off, the frequency is going to go down further. So, you know, there's a problem there. A lot of this stuff materialized as we gained experience over the decade after this standard was issued, which was 2003. And that caused us to write amendments to the standards that were issued in 2014 and 2015. Oh, one other you also have to coordinate this. This is something you can throw out your physics professor sometime. You have to coordinate with a device that's called a recloser. And they are automatic devices that are on a distribution line that says if I have an unacceptable operating parameter downstream of this device is going to open. And then it's going to reclose. Now, many distribution companies do an immediate or an instant reclose, which takes about 12 cycles. And the reason it takes 12 cycles is that's the equation, empirical equation for the time it takes for the environment of an arc to dissipate so that when you re-energize the line, you don't reignite the arc. It's 10.5 cycles plus system voltage divided by 34.5. This was developed empirically probably in the 30s and was part of the Westinghouse station engineers textbooks. So you need to coordinate with their system. You have to get off, if you got a synchronous generator, you got to get off the line before that recloser comes back in again. So typically a 9-cycle clearing time will do that for you. Clause 4 is power quality. I don't know how you determine this. In the functional requirements to qualify a product, you feed it at 1/3, 2/3, and full load into a defined impedance load. But when you get to a job site, if you measure the utility voltage, it's going to have a lot of harmonic distortion. And when you connect your distributed energy resource to it, it's going to have a lot of harmonic distortion. It may have less than was there before, it may have more than was there before. The problem is you don't know who's doing it. So there is a standard that says this is what it shall be when you qualify the product. And the basic presumption on electrical equipment is they look at immunity, immunity and emissions for conducted and radiated harmonics. So your immunity, you have to be immune for upwards of 8% harmonic content. And emissions, you can't emit, depending upon the frequency, you can't emit any more than upwards of 4 or 5%. So that little 3% variant there is what is presumed to give you a buffer for allowing for standard operation. Clause 5 is the testing. It says that every product has to have a design test. Now, .1, 1547.1 is the standard that establishes the protocol for design testing. If you're developing a product for application, you have to state the environment that that product is good for. So, in my experience, in the NEMA environment, it's 0 to 40 degrees C temperature. And it's upwards of 95% non-condensing humidity. So when you test your product, you test it at 0 degrees, at mid-range 25 degrees, and at max 40 degrees C to see if your device operates. And if it's an adjustable device, you would evaluate it at the min, mid, and max setting of the range at those 3 temperatures. And if it had a time function in it, you would measure it at the min, and max parameter, mid, mid, and max time, mid, and max parameter voltage, temperature rather. So that's a lot of testing. But you only do it on one product, and you're generally doing that while you're developing the product anyway. And it's a standard requirement in order for it to get a listing to UL, which is required by the National Electrical Code. So it's not an encumbering requirement in the standard. Production test, again, agencies like UL in their standards, they require that you run a production test on a product so that when it ships out the door, you know that it was working and you know what the setting for it. Response to abnormal. Commissioning, this is not really a test. And it's semantics, I will admit. But commissioning is not a test. All your testing is done by the time you're going to commission one of these plants. This is an evaluation of the installed site. These are the things you're going to look at. Is the equipment qualified? Is it listed? You do a visual inspection. Does the installation match the drawing design? Is it in accordance with the utility companies and your signed agreement as to what you're going to be doing at this site? And then you would do some functional testing like a non-islanding test and a cease to energize test. Now, Dave and I had a conversation about this a few minutes before we started here. One of the problems that I've run into when we're doing an evaluation of the system to see if it's functioning properly is doing a single facing test where you just open one of the feeders going to the system to see if it detects that single facing. But one of the things that can trigger is called a ferrule resonance situation, where the outed phase, due to the capacitant coupling in the system and the inductance of the outed coil of the transformer, can produce a resonant circuit that can give you voltages of 12 to 15 times the normal operating voltage. That's not good. So when we go to do these single facing tests and so on, we need to do a real evaluation to make sure that we're not going to trigger a ferrule resonance situation. So when we did 1547.1, we had fewer people doing that, 115, 7 members, and I picked the members of the writing group. And then we had a 115 balloting group, and they passed very well. We validated 1547 at the Department of Energy's test site in Nevada. You guys have heard of Area 51? That spook place the Air Force and wherever else housed out in the desert in Nevada. Well, we did the testing at a section of that site called Area 26. And Area 26 is located, this is true, you can look it up on the map. It's located in Jackass Flats, Nevada. That is the name of the section, believe it or not. You can look it up on the map, go to Google and look up Jackass Flats and we'll show you where it is on this test site. So we were able to validate because we had a section of the site that was shut down. We could turn it on, we provided power to it. We were able to make adjustments in the grid and whatnot so that we could evaluate the requirements of the standard. And it proved to be, we proved the standard requirements out. They were validated. And then, of course, there's some papers that we wrote showing the results of the test and whatnot. 1547.1, again, technical requirements, and I went through the various steps that you have to go through. I want to jump ahead here and get to what we did just recently, which is the amendment to the standards. This we started in 2012, I think it was. Now, what we learned in the 10 years between 2003 and, well, 9 years, 2012, was that indiscriminate disconnection of distributed resource, renewable power had negative impacts on the system. One of them we saw in this incident that occurred in California. But I'm going back to about 2007, 2008, there was a section of the transmission system out in the west, on the western grid, that had a fault and a depression in voltage that lasted 20 seconds. That doesn't mean it was down for the 20 seconds. It means it had an initial drop to like 0.6 per unit voltage, which is 60% of nominal. And then it took 20 seconds for it to come back up to the 0.9 per unit or 90% voltage. And in that period of time, because the standard said get off in 2 seconds, they lost a lot of renewable energy systems on that transmission distribution system. And the net result was it led to the 20 seconds of depressed voltage. So what the Federal Energy Regulatory Commission did was they said that we're going to change those requirements. Now you have to ride through low voltages. So if the voltage goes down to 60%, you got to stay online and continue to provide power during that time so as not to worsen the event. If you go down to considerably below that, then you can get off the line. So these experiences, and this caused us to have to amend the standard. Now, we amended the standard in three cases. One is it was now permissible, not only permissible, but desirable for a distributed energy resource to contribute to voltage regulation at the point of usage, not so much by actively regulating, but by providing VARs into the system to compensate for excessive VAR draw where it is located in the distribution system. And this sounds great. I mean, as far as the utility operator is concerned, it's a really good thing. But the problem is that a solar photovoltaic system and a wind system make their return on kilowatts. Not on kVA, not on kilowatt, but on kilowatts. So if I have a 10 kW solar farm, that's 10 kVA. And if I say all of a sudden, instead of giving me 10 kilowatts, give me 6 kilowatts and give me 8 kVAR. Well, I'm only paying for the 6 kilowatts. I'm not paying for the 8 kVAR. So the problem is the return on investment goes down the tubes. So now you have to get into creative rate establishing and operating scenarios that don't detract from the return on investment, but also accommodate what the utility system needs for stability. And there is a cost advantage to the utility system for getting VARs from a distributed energy resource system. So this is the working group that developed it, and these are all engineers and regulators and whatnot. And I was given an award for getting us through. I was given 3 meetings to get this standard amendment rewritten and out to ballot. Got to do it in 3 meetings, both .1 and 1547. And I managed to do it. But you know what it's like to try to keep 40 or 50 engineers going in the same direction, having the same conversation at the same time? As a result, I was awarded a t-shirt that said National Championship Cat Herder. Because trying to keep their attention on a single point was like trying to herd cats. So now we have a standard that allows for VAR output, that allows for voltage ride-through, and allows for frequency ride-through. The old standard said the system shall not operate to regulate voltage at the point of connection. Now it says that the system can provide VARs with the mutual agreement of the system operator and the renewable source operator. And these are the differences in the voltage settings. This is 1547. And notice if you went down to 50% voltage, you were off in 10 cycles. 50 to 88, you were off in 2 seconds. 110, you were off in 1 second. And over 120, you were off in 10 cycles. Down here, look at the range of adjustability. There was no range of adjustability on those. Now, you can have up to 21 seconds at a voltage between 88 and 60%. So you got to stay on the line for that 21, up to 21 seconds to coordinate with their system if you're running at 0.6 per unit voltage. These were the numbers that came out of FERC. We did the same thing for frequency because the way that the utility company saves the system from catastrophic shutdown on an overload or large loss of generation is by, as the frequency goes down, it starts shedding huge blocks of load. So here we get into a situation, well, we don't want to shed the generation when I've got a frequency that's going down. That just exacerbates the problem. So I'm going to keep that generation on for lower frequencies. However, when I have a situation where the frequency is going up, then I want to shed some of that renewable energy input so that I can keep the system within frequency, within the proper frequency range. We are currently under development of the next issue of the standard. It was balloted and it is in rewrite right now and soon to be put out for reballot so that it can go on to standard. You said communications, right?
Yes.
So that we can communicate,
Yes.
right?
Correct.
Okay. What would that look like? For one user, PPL has over 140,000 users. Does this look like something that's manageable? And this particular standard, 2030, well, it's not a standard, it's not even a guide, it's an evaluation of what the impact is of trying to achieve this communications. It's just a real challenge to come up with something that is manageable and realistic in terms of how you're going to apply this smart grid concept. My opinion, and I expressed this to the standards writers at the last working group. What you need to know from a distributed energy resource is the system operating? Isn't it? Is it online or isn't it? And is it connected or isn't it? Now, the utility company with smart meters can disconnect you. So what you want to know is if I told it to disconnect, did it disconnect? And that's the feedback loop here. So basically, this is what you need in order to do the fundamental integration of smart grid. The next thing is, and this gets hairy when you start looking at, I want the distributed energy resource to provide VAR support at its point in the distribution system. Well, how do you do that? Do I go out and tell him to switch to all VARs, part VARs? Do I tell him to go out and switch to some unity power factor, 0.9 or 0.8 power factor? Do I communicate that based on, I know time of day that this is going to happen, so at this time I want bars? There are a number of different scenarios that you can introduce on how you are going to turn on and turn off bar support at the point of connection in the distribution system. All that stuff's got to be figured out. I'll tell you a story, and I'll show you the system. Yeah. This is a combined heat and power system. There are two 1.8 megawatt generator, 1.9 megawatt generators up here that are gas fired, and a 2 megawatt diesel, which is an emergency generator. These are CHP generators, combined heat and power. They recover heat to produce hot water for the hospital. Now, all of the protective relaying setting in here in this primary feed is a service to the hospital, and then this is the feed that serves the rest of the switchgear from the generator, generator bus. Now this system's in operation for 3 or 4 years, and all of a sudden at 7:30 in the morning, their diesel starts up, they disconnect from the utility, 15 minutes later they reconnect to the utility and shut the diesel down. But they disconnected the gas generators too. And then the next day, Tuesday morning, 7:30 in the morning, go through the same exercise. Wednesday morning, they go through the same exercise. That is something that's, systematic in this. Come to find out that the utility company was going to service this distribution feeder from the substation. So they took this feeder and put it on a different substation that wasn't as strong as the original one. And what they did in the mornings, because it's summertime, they put capacitive K-bar correction on here, which caused the relaying here to see an overvoltage, which caused it to disconnect and go through this emergency operation. So with all the good intention of all the settings that we worked out in the original design and whatnot, we had to come back and increase the overvoltage trip points on this relay and this one here so that we could accommodate this particular requirement. You're not always done when the system goes in. This is 5 kV bus, turbine generator, 4.5 megawatts, heat recovery from the exhaust gas. 5 MVA transformers here, and this one was put in for this bus. Originally, it was a delta Y transformer, but the utility company said we only allow YY connections. So they pulled out a 5 MVA transformer, 60, 70,000 pounds, and replaced it with a YY connected 5 MVA transformer, fired the system up, and took the system offline because the generator was a 4/5 pitch machine. It doesn't mean anything to you. What it means is that with a Y connection, it produced a lot of third harmonic current, like full load third harmonic current on the neutral that flowed into the system, and therefore we couldn't load the machine to anything more than 1,500 kilowatts. So we had to go back and revisit this transformer and the system in order to solve that problem. This one is cute, it's unique. This comes from 2 different substations. And when they're going to switch from one substation to the other, they parallel these 2 feeds. They close both in breakers. The utility company does that. But there's no telling that both of those substations are at the same voltage or at the same reactive bar setting, or that you won't have a pretty significant swing of currents between the 2 of them in order to go through your transition. So This was just, I had never seen that done before in a customer switchgear, but they seemed to think it was okay, so anyway. Okay. I think I finished on time.
We've got time for questions and answers. Anybody questions? Somebody has a question. I'm the only non-scientist in the room, so go
Sure.
ahead.
Could you talk a little bit how, what kind of problems that could occur? I'm doing I'm in the SCI program in my project. I'm performing hosting capacity analyses.
On what?
Hosting capacity analyses on distribution feeders for PV solar, and I was wondering if you could talk a little bit about value problems that are associated with too much solar related to those interconnection issues.
Well, you can never really have too much solar. It
Depends on your point of view.
It's really driven by return on investment. As far as the host is concerned, if you have a customer, a metered customer, and you're going to put solar into his facility, then the question becomes how much money is he willing to invest in it, and what is the return on the investment given tax credits and whatnot. But generally speaking, if you keep it to his peak demand or less, you'd probably be okay. But I think you're going to find that the limiting factor is going to be the cost, the return on investment.
It depends on jurisdictions and what the rates are. In New Jersey, that I'm familiar with, the rates allow you to, or at least the rate for my utility allows you to install enough PV so that over the course of 12 months, you're neutral. You're not generating more on the PV than you're using with load.
I'm still listening, I'm writing.
As long as you do that, then you get the sweetheart deal of getting paid at the retail delivery rate for your output. If you exceed that over a 12-month period, now your compensation is going to drop down to the PJM commodity price rather than the retail delivery price. So that's one limitation. And when you say hosting, are you looking at a facility as hosting, or are you thinking of the EPS that it's connected to?
Yeah, I'm working primarily with 10 distribution feeders attached to 3 different substations.
So you're looking at the EPS load.
Yeah, so we're looking to increase the penetration of solar to 50% peak load.
So we've got some things like voltage control, and voltage control as the clouds come in, those darn clouds, and how the solar is going to interact with the loading and the operation of the utility system. Is it permissible to have energy go backwards through the transformers in those substations? Can you go from distribution voltage to transmission voltage? Does the relaying allow that? What does the ISO think about that? And then shy of that, some utilities might set thresholds both for individual feeders and for transformers that serve multiple feeders for what the level is. So what James was talking about was some of the different voltage control in inverters. There's a question, could that help for large solar connections to manage voltage and allow higher penetration than you otherwise would be able to tolerate?
I can tell you from my experience with hospitals and computer centers and whatnot that do CHP, it is never cost effective to produce all of your energy and sell electricity back to the grid. It is never cost effective to do that. And there are a lot of projects that
Well-
thought that it was and went belly up.
And
Big
James-
bucks.
One of the problems is if you do that, now you've got to pay the lawyers to write the agreements that support that.
If you're talking about, when you say the hosting facility, the picture in my mind is a Walmart store with roof solar units, or a manufacturer with a canopy over his parking lot and solar units on it. I think you're going to find the cost of solar per kilowatt, the investment would not be repaid if you were looking at producing all of your energy. What solar and wind do is they produce energy. They do not produce capacity. And if you're going to meet your energy need, you're going to pay for it in capacity because you're going to have a negative impact on the distribution system feeding your facility. So if I were you, I'd sit down and talk with a utility company that has well, they all have established interconnection requirements. And in there, in fact, PPL, you can go on the internet and find PPL's interconnection requirement. I would suggest that you stay away from California. And I'm only saying that so that you keep your sanity, because, what is it, Rule 29?
21, I think.
Rule 21 is 530 some pages. Yeah, and they've got caveats in there that you wouldn't believe. Go for someplace simple, PSC&G, PPL, JCP&L. You're not going to come up with something that's universally applicable across the country, because the generation, transmission, distribution systems vary widely across the country, because the demand profile varies widely across the country, both seasonally, daily, and so on. So if you stick to this area, you probably could come up with a pretty good paper.
Yeah, and the project is sponsored by PPL, so all those 10 feeders are out by PPL.
Oh, look at their interconnection agreement and base it on that. They have a breakdown at 20 kW, 100 kW, and I think in excess of 500 kW. So it's going to depend a lot on the size of the system as to what caveats and restrictions are going to apply.
Thank you.
Nobody here is going into electric generation. Give up a great opportunity for a great future. All us old guys are retired. They need people to replace us, and they're looking hard for them. Thank you.
Thank you.
Thank you very much, Mr. Daley. If you have your surveys, just leave them for me up